Good morning, everyone. This is Mr. Couple. Today I'm here with my physics class, and we're going to be learning about magnetism. Say hello, everybody.
Hi.
Hi.
We got Ben, we got Jamie, and we got Mayar, but Mayar is afraid to talk because her mic is having problems. All right, so I want to show you guys this picture of these stones. And this is sort of a story. So before I go into the science and physics of magnetism, let's have a story. So thousands of years ago, these stones were found and they were weird. Like, do you guys see how there's something unusual about these stones? Like, what do you notice that's different about these stones than like typical stones?
They're spiky.
Yeah, they got these little like bits of stuff sticking out of them. Well, that's actually not part of the stone. Those are small little pieces of iron that are stuck onto the stone. In fact, over here in the picture on the right-hand side over here, you can actually tell that these stones are actually attracted to each other. And you can even see like there's a ledge right here and the stones are hanging attached to each other off the ledge. So this is a big discovery thousands of years ago by the ancient Greeks that there are actually these stones that were attracted to each other and were attracted to little pieces of iron that would get stuck onto them. These stones are found in this region of Greece called Magnesia. So this region right there was called Magnesia. It was a small coastal region in what I call it in a place called Thessaly in ancient Greece. So the word magnet isn't a scientific word. It actually just referring to this location, this region where these stones were first found. So the word magnet comes from the Greek word, I'm going to completely mess up the pronunciation, but magnetos lithos, and that means magnesian stone. So when you say the word magnet, you're not saying anything like scientific or like any fancy vocabulary word like that. You're literally saying, referring to this location in Greece where these stones were first found. Isn't that cool?
Yeah.
Sure.
I mean, I always thought it was interesting that like there's no deeper meaning of that word magnet. It's just referring to this place.
If you look deep enough, nothing means anything.
Wow. Okay, I'm so sad now. I'm gonna go cry myself to sleep tonight. Okay, so here's a cool picture. This is in a museum in Germany, and you can see this stone. And this is what a lot of students don't realize is like you don't magnets don't have to be manufactured. I mean, you can manufacture them, you can build them in a factory, but you can also just pick up rocks off the ground, and they can, if you're lucky, they can be a magnet. So here's an example of an ordinary looking rock, like a stone, that's clearly exerting a force on these paper clips and pulling them towards the rock. So there's this attractive force that this rock is exerting on these paper clips. And so this force is called the magnetic force, and it's what I'm going to be trying to teach you guys about today. As you know, magnets come in many different shapes and sizes. I'm sure you all have played with magnets before when you're a little kid or maybe even recently. But what you'll notice, like no matter what shape or size a magnet is, that there's always something that every magnet has in common. And that is that they always have two poles. There's a north pole and there's a south pole. No matter what shape or size a magnet is, it will always have these two poles. Or rather, I should say, we have never seen a magnet that doesn't have two poles. I'm not saying it's impossible for a magnet to have one pole, but we've just never observed it before. And we've tried. We've tried really hard to find that, and it's never happened. There are two types of magnets that you guys are probably familiar with, like the common magnets. Those are the horseshoe magnet and the bar magnet. Now, I realize that a horseshoe magnet is just a bar magnet, but it's been bent so that the ends are near each other. And so you bring these two poles right near to each other, and what happens is you can get a much stronger magnetic field created inside that space. So that's the benefit of a horseshoe magnet is like by bringing the two ends closer together, you get a stronger magnet in that local area. And on the other side of the magnet, there's no field at all. Like there's no magnet on that side. Can you guess the magnetic force rule? So what do you think will happen if I put two North Pole magnets next to each other? What will those two magnets do to each other?
Repel.
They repel. And then what if I have opposite poled magnets?
They
What?
slam together.
Yeah,
They
they
slam
attract each
together.
other.
I let my hand off the mic.
So that's the magnetic force rule. And so realize like this is this is really similar, right? That we have the same thing as before. So opposites attract. And when I say the same thing as before, what am I referring to?
Charges.
I'm referring to the charge rule. And then likes repel. It's the same rule as the electric force. So this does look familiar. Why did I cover this up? It's the same rule, the same force rule as the electric force. But you got to be really careful, guys, because they're not the same force. The magnetic force and the electric force are two different things. They're very much related to each other. We call it the electromagnetic force. And we'll talk about why a little bit later as we go through the next couple of weeks. But it's really important that you realize that magnetic forces and electric forces are two different things. So don't confuse charges and poles. Magnetic poles have a magnetic force, but it's electric charges or charged particles that feel the electric force. So don't confuse those two. It's really tricky. Here's a picture. So what we're going to do here to make this, the way this picture was made, is you take these things are called iron filings. So that's these things over here. They're little tiny bits of iron, like you saw them in the picture at the beginning on those stones. And what we're going to do is just sprinkle these filings, like sprinkle them down around this magnet. And you end up getting this really cool pattern. What does this remind you of?
Electric fields.
Yep, it reminds us of electric fields. So magnets create magnetic fields. Just like electric charges create electric fields, magnets create magnetic fields. So check out this cool video. I saw this on Reddit a couple months ago. So we take this really powerful magnet and they're showing you, and then you hang it, and then we flick a bunch of filings up at the magnet. And you can actually see when you slow down the video, you can see that the magnetic field is existing in this space surrounding the magnet. And so the filings are having a force exerted on them by the magnet. And so the motion and the arrangement of those filings is showing us the magnetic field that center magnet is creating. I think that's just a really, really cool video.
That would be horrible to clean.
Yeah, it would be. Looks like they have like a big mat, like a big mat down, but I'm sure some of them got off to the side. Also, when those filings get stuck on the magnet, they're really hard to pull off.
That's
Yeah,
what I
so
meant. The magnet would be horrible to clean.
yeah. So if we were in the classroom, I would have actually had you guys do something similar to this, where we took these filings and sprinkled them around a magnet. But this is the best I can do with the remote learning. What direction do magnetic fields point? So we've talked about, like, with charges. If you remember, I should probably recap real quick. So if you have an electric field, I do it in green. So if I have an electric field like this, we use E for an electric field. So you say, hey, how do I know that that field is pointing to the right? Or what does it mean to say that the electric field points to the right? Well, we say that if you have a positive charge, it's going to get pushed to the right. Whereas a negative charge would get pushed to the left. So the direction of the electric field is a direction a positive charge would get pushed by the field. So we have a similar rule for magnetic fields, but it's a little bit trickier. So what direction do magnetic fields point? Okay, so check out this video. So if you bring a bar magnet near to a compass, really cool, weird things happen. It's like almost magical. So you can actually move the compass needle with the magnet. And we're also used to compass needles, pointing towards the Earth's North Pole, that we don't realize that actually what compasses do is they point towards any magnetic field. Compasses align themselves with a surrounding magnetic field. So why does this happen? So the truth is that actually this little tip right there, the needle of a compass, is actually a magnet. And the north pole of its magnet is that little painted red side. So we're trying to explain why the compass is moved by the magnet. So there's three things you need to know, and I'll just reveal them one by one, and then hopefully you guys will understand it. So first, a compass needle is just a magnet. That's all it is. It's just a magnet. There's a north pole that's painted red, and the other side is the south pole. So remember, this is going to be important. So this is the north pole. Do it in white. So this is the north pole, and then this is the south pole. So a magnet has two poles. The needle of a compass is just a magnet. Okay, second thing you need to know. What this means then is that a magnetic field will exert a force on a compass needle. Since a compass needle is a magnet, if it's placed in a magnetic field, the magnetic field will exert a force on it. And so that's what you're seeing up here is like the compass needle is a magnet. This bar magnet is creating a magnetic field. and then that magnetic field is exerting a force on the compass. Lastly, compasses can be used to detect magnetic fields. So since compasses are what we use, it's a device that we've created. It's an ancient device, like that was created thousands of years ago. This is how we measure magnetic fields. So instead of talking about like how a charge would move around through an electric field, we instead talk about how a compass needle will move around in a magnetic field. So the compasses are the basis by which we understand the direction that a magnetic field is pointing. Here's an explanation of what's going on. So if you have a compass needle and it's not aligned with the field, so that's what's happening in this picture here. So the compass is not lined up with the field. You can see the field is going up and down, but the compass is at this angle. Then what will happen is the magnetic field will exert a force on the compass that will twist it. It's called a torque, like a twisting rotational force. And those forces will pull and they'll make the compass needle rotate. And it will rotate until it's aligned with the field. And so that's how the compasses align themselves with the magnetic fields. What's up, Ben?
Yeah, you've frozen
Frozen? Thanks for telling me.
for me at least.
I'll reset the
Yeah,
stream.
Yeah.
Looks like I need to move away from Discord. They're having problems. Okay, how are we looking now?
It's on.
Okay, cool. How much did you guys miss? Did you get that part about how the compass will have a twisting force on it? The needle will have a twisting force on it. But then once it's lined up with the field, that force is no longer able to twist the compass.
Could you
yeah,
go
we're
over?
hearing you.
Say again?
Could you go over it again?
Yeah, sure. Can you guys see the stream right now?
No, I can't see you. I can only hear. The screen is black.
I'm going to try one more time resetting the stream. How about now?
It's thinking. It's thinking. It's thinking.
Yes.
And it's on.
Okay. All right, so what I was saying was that a compass needle, when it's not lined up with the magnetic field, see the magnetic field are these vertical lines. When the needle's not lined up with the field, there's going to be a rotational twisting force that acts on it. So the field's going to try to pull it in the direction of these arrows. And that's going to end up causing the needle to twist, or I think I did it the wrong way. It's going to cause it to twist. This is called a torque, a twisting rotational force. So then it'll get twisted and pulled until that force is in line with the field. And then the compass needle will stop moving and it'll be stuck there. And now it's pointing in the direction of the magnetic field. So here's something that's really weird. Compasses don't always point north. This is what you think because that's how they point on Earth. They point north. Well, at this point in time, they point north. But if you went back like a million years ago, they didn't point north. Even a couple 100,000 years ago, it didn't point north. So compasses point away from magnetic north poles. That's what this little experiment is showing here. I would have had you guys confirm this in class. You can see that arrow right there, the compass is pointing away from the north pole. And over here, the compass is pointing towards the south pole. Now, this is really, really weird. But this is how compasses point. Compasses point away from magnetic north. So if you have north, the compass is going to point away from north. And if you have a south pole, it's going to point towards the south pole. And that's kind of the opposite of what you'd think, because you think compasses point north. Well, they point in the northern direction. They point towards the north on Earth. But that's not how they actually work. Compasses point towards magnetic south poles. All right, so here's a picture of a magnetic field surrounding a bar magnet. And then what I'm going to do is I'm going to grab a compass and I'm just going to place it in the field because we want to try to figure out what direction the field lines are pointing. So I'll show you the first one. So I know that compasses point towards the South Pole. So I'm going to grab this one and place it right there. So that's the direction that the compass is pointing towards the South Pole. So it means that all these field lines over here, they're all going to be pointing towards the South Pole. On the other side, at the North Pole, it's going to be pointing I need the same compass. I got to copy it. It's going to be pointing away from the North Pole on the other side. So there's my, I don't know why the black got carried over as well. What are you doing? Come on. Give me this. Bring it over here. What the heck? Let me try that one more time. So if I grab this guy, paste it down. There we go. I don't know why the black got copied. So that means that the field over here is me pointing away from the North Pole. Okay, so now I have a question for you guys. What if I place the compass here? What direction would the compass needle point if I placed it in the middle?
Vertical?
So up like this?
I feel like this is a trap, but
I
yes.
I think it'd be the same because compasses work everywhere except for on the poles because they're weird there. But I think it'd be the same as the edges as where the first two ones are.
So it would point like this one?
Yeah.
Like that?
Yeah.
Okay, so let's try to figure it out. So here's what's going to happen. If you have a compass here, if you have a compass needle, I'll just draw the needle like this. So what's going to happen is the North Pole of that needle is going to get pushed away from this North Pole. So that means that it's going to try to repel it away. So you're going to have a force that way on the North Pole, but then the North Pole is also going to get pulled towards the South Pole. And remember, this side of the magnet is of the compass is the North Pole. So our North Pole is going to have two things happen to it. It's going to get pushed away by this North Pole, and it's going to get attracted to this South Pole. So what would be the sum of those two forces? If you have one force pointing up that way and another force pointing down that way, what would be the sum of those two?
Backwards.
This way? If I add these two things up, so imagine you have like an object right here, and I pull it this way, and then I also pull it this way. What direction will that object move?
It's gonna go in the middle.
Yep, it's going to go like that. So that's actually the direction that the compass is going to point right there. The compass would actually point this way, which means that all these fields here, you can see the field lines, they're pointing in that same direction. They're pointing to the right. They're pointing away from the north and towards the south, but that ends up being in the middle of the two. So it's a little bit weird. All right, so let me show you proof of this. So here's what happens if we put a bar magnet in a compass field. And I want to figure out which of these poles is the North Pole. So which pole of this magnet is the North Pole? Ideas, thoughts?
The red one, because the red one's always the north one.
That is how we paint it, but it's not. We don't know that for sure because it's just someone painted it. But if you drop a magnet, you can actually reverse the poles. You can flip them, or you can even if you drop a magnet, you can even make it not be a magnet anymore. But this is the North Pole. So what's the evidence here that tells us that this is the North Pole? When you look at all the compasses, what do you see?
The arrows on the compass are pointing away from it.
All those compasses are pointing away from that North Pole, and then they're pointing towards this South Pole. And then you can see in the middle here, in this middle area, they're all pointing horizontally towards this South Pole over here. So this bar magnet is opposite of the one that I was showing you guys up here. So ours was pointing to the right, towards out of the north and into the south. And that's what's going on down here. The field comes out of the north and into the south. I think this is a really cool picture. All right, so here's a big question. What the heck? Why do compasses point north? If compasses point towards south poles and away from north poles, then why the heck do compasses point north? So this is a really confusing question. It drives students crazy every year. They have a really hard time understanding this. So I'm going to try to do my best to explain it to you guys. Okay, number one, the Earth is a giant magnet. Now, do not confuse a geographic pole with a magnetic pole. We use the word pole, but there's two types of poles. There's a geographic pole, which is usually called the North Pole. It's a location, it's a place. It's like on a map. You could find the geographic North Pole. So there it is. This is defined by the rotation of the Earth. So as the Earth is spinning around and spinning on its axis, the tippy top, the point that's not spinning at all, is called the North Pole. And then the opposite to that is called the South Pole. But those are the geographic poles. Those are a physical location on the Earth where the rotation of the Earth is zero. So if you stood there, you wouldn't be moving around in a circle. You'd be just staying in the same place if you stood at the North Pole. The magnetic pole is based on the Earth's magnetic properties. And it turns out that north of where we are, so if we're here in Kansas, if that's where we're located, then north of us, you find the Earth's magnetic south pole. So it just so happens that for random reasons, the magnetic south pole of the magnet Earth is located at the geographic North Pole. And so that's why compasses point north, because they're pointing towards compasses point north. That's what I'm reading this down here. Compasses point north towards the Earth magnetic south pole. What questions do you guys have for me about that?
Cool.
Ace.
So it's super strange that compasses actually point north because that's where the south magnetic pole is located.
Do your students actually have trouble with this usually?
All the time, yeah. I guarantee you right now, people watching this video are having trouble. This is a difficult concept to understand. Okay, check this out. Let's distinguish between magnetic poles and charged particles. This is really, really important. So it turns out that magnets always, like I said before, have to have two poles. So you're allowed to have that. This is allowed. Maybe I should like make it bigger. So you're allowed to have this. This is allowed. But these over here, not allowed. You can't have this and you can't have this. You can't have, I should probably like let you see that there's like, okay, there you go. So you can't have a magnetic pole that's hanging out by itself. They always have to come in pairs. So it's okay that like you have a north and a south next to each other, but you can never just have a north. You always have to have a north and a south. They always have to come grouped together. Is this same rule true for charge? Are we allowed to have just
No.
a single positive charge? Are we allowed to have a single positive charge? Yes or no?
Yes.
Yes. Are you allowed to have a single negative
Yeah.
charge?
Yes.
Are you allowed to
Yeah.
have are you allowed to have a dipole of charge?
Yeah.
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 So this is what's strange about magnets is that magnets aren't allowed to exist on their own. They always have to have two poles. Magnets have to have two poles. I'm emphasizing this because it's a really important idea. So they act like very similar, opposites attract, likes repel, but magnetic poles are fundamentally different than electric charge, and you have to understand that. Okay, so every magnet has to have both a north and a south pole. So what happens if you break a bar magnet in half? So what would happen if I took this magnet and I just snapped it in half? What would happen? Would we get a north pole hanging out by itself and a south pole hanging out by itself? Is that what would happen?
You got new north and new south poles, but they were there all along, but they weren't, but they were, but they weren't, but they were.
So this is what would happen.
Yeah.
You get two magnets. Yep. So if you take a single magnet and break it apart, you can't have a north pole by itself. So what will happen is a south pole will come up on the other side of that magnet. So taking a single magnet and breaking it apart ends up creating two smaller magnets. Magnets always come in dipoles. They always come in two dipoles, two poles, no matter what. Okay, the reason for this is quite complicated, and I don't know if I'm going to fully be able to get to it, but let's talk about where magnetic fields come from. So magnetism is very much related to electricity. We call it electromagnetism. They're two parts of the same coin. So it's like, one side of the coin is electric and the other side is magnet. You combine it together, it's electromagnet. So they're deeply connected to each other. So here's the thing. What happened to my charge picture? I don't know what happened to it. All right, but anyway, so what I have here is I have a charge, and the charge is surrounded by an electric field. So I'll use E for that. So this is my electric field. But if that charge is moving, in addition to an electric field, it will also create a magnetic field. And so this is what you need to know, is that moving charges, I don't want such a big pen. Moving charges don't just create electric fields. All charges create electric fields, but moving charges also create magnetic fields. I should say create. Moving charges create magnetic fields. So it turns out that all magnetic fields, no matter what, the source of all magnetic fields are moving electric charge or moving charge particles. So for example, this proton is moving. When the proton moves, it has, in addition to the electric field around it, it also has this magnetic field. Now what's confusing and complicated is that the magnetic field makes these weird like circular patterns to it. They're circles. Remember the circle thing because it's going to come back a little bit later. But a moving charge creates circular magnetic fields around it. And that's the most disgusting picture I've ever seen. But that's what it looks like. It's really complicated. So if you have a bar magnet, you got a normal old regular bar magnet here, then where are the moving charges inside a magnet? That's kind of strange. Well, it turns out that it's actually inside the atoms that the magnet is made of. So there are two distinct types of motion that charges can have within an atom. So the nucleus stays fixed, but the electrons actually whirl around the nucleus, and they also behave as if they're spinning. Like they're like a top, like spinning. So they could be spinning around, but they also are moving around. So here's the picture of those two things. So spinning electron and an orbiting electron. So you can have this spinning motion and this orbital motion of the electrons going around the nucleus. So that's where the motion is that's creating the magnet inside a bar magnet. So there's two types of motion that electrons exhibit. All right, so every spinning electron is basically a teeny tiny little magnet. If you take a charged particle and you spin it like a top, it'll be the world's smallest magnet. It's the smallest possible magnet. So if you have two electrons that are both spinning the same direction, so they're both spinning around like then that means if they're near each other, you're going to get a more powerful magnet. So they're going to get a stronger magnet. But what if you have two electrons that are spinning the opposite way? So one spinning clockwise and the other one spinning counterclockwise. What would happen then? You wouldn't get a stronger magnet, but you would end up getting, they would work against each other, and then the fields would cancel out. You'd end up getting no magnet. So they would destroy each other. So now I'm going to try to explain to you guys some quantum physics. Whew. All right, over here, this picture on the left-hand side, this picture is what the orbits look like for where electrons can be around an atom. There's this thing called the electron cloud. And so here we have all these electrons just randomly moving around the nucleus. The nucleus is the dot at the center. Then there's all these different allowed orbitals. There's the s orbital, the p orbital, the d orbital, the f orbital, and then there's various levels that they can be at, first, second, third, fourth level. So these are the different pictures of what atoms look like according to the laws of quantum physics. So this is what iron looks like. So if we look at iron, now iron is a magnetic material. Iron exhibits magnetic properties. So first up, this is argon. So see these boxes here? These boxes represent the electron orbits. And so each box can have two electrons in it. One electron can be spinning up, and then the other electron can be spinning down. And that way they can both fit in the same box. So argon looks like this, but iron has an extra 6 electrons in the 3D orbit. So I'll add those 6 here. There's 1, 2, 3, 4, 5. Now we've ran out of space. So now the electrons start packing in more. So we can fit in a down right there. That's 6. And then 2 electrons in the 4s orbital. You guys are going to learn all about this when you take chemistry. I just thought it'd be fun to show you here. So what ends up happening is that there's 4 electrons over here. There's 4 electrons that are not being canceled out by any other electrons. And all the other places, though, there's an up and there's a down. And those electric fields, the magnetic fields created by those electrons cancel out. But you have 4 up here that aren't canceled. And so that's why iron exhibits magnetic properties. But if you look at something like copper, what happens with copper is that d orbit is completely full. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then there's 1 s. But that s is kind of buried down there, and so copper doesn't have any magnetic properties. Like all the electrons have a partner that's going the opposite way. and then this S is buried below there, so like you don't really notice the effects. You only notice the magnetic effects when the electrons are out far from the atom. Okay, that's too complicated, but you'll learn more about that in chemistry. All right, so what I'm going to do now is show you guys a microscopic view of iron. No, my timer. Okay, that means I got to wrap it up. This is a microscopic view of a sample of iron, and what you'll notice is you'll see these little crystals, like these little regions, like these little crystal regions within there. So what happens is the atoms that are inside there. So realize there's a bunch of atoms in here, and those atoms have electrons in them that have 4 extra electrons that are creating a magnetic field. So each atom in that region is going to exert a strong force on the atoms around it. And so what ends up happening is all those atoms end up having the electrons all spinning in the same way. And so we could put an arrow there showing that's the direction that all the electrons are spinning, and they all line up. And so these clusters are called domains. They're called magnetic domains. And this is what happens inside iron. So each domain acts like a tiny magnet. And so you can see like there's all these different regions, these crystal regions within the iron, where all the atoms and their electrons are all lined up and spinning in the same way. But if you look at this on if you look across the entirety of the object, for everyone that's pointing down the left, you can find one that's pointing up to the right. For everyone that's pointing, let me find one, down like this, there'll be another one that's pointing exactly opposite to that, like this. And so as you look across the entire object, if one's pointing to the left, there's one pointing to the right. You can always find another domain that'll cancel out the domain that you're looking at. So the net effect on the whole is that there's no overall magnetic effect. But remember, those domains are acting like tiny magnets. If you bring a magnet nearby, so if I have a south pole of a magnet here, now these domains are placed within a magnetic field. So now what happens is all those electrons, all those domains, they'll actually line up with the field. And now what you've done is you've magnetized the iron. So this is called magnetized. When you remove the magnet, the fields, because random molecular motion, like due to the temperature effects, those atoms will start to move around and knock into each other. And when you remove that magnet, it's like up here in the second case, if we remove the magnet, they'd go back to being random again because of the random motions of the particles. They'd get kicked out and then they'd be all disorganized again. But as long as that external magnetic field is there, as long as you have this magnetic field from the bar magnet, they'll line themselves up with that field. All right, so this explains how you can magnetize a nail. So you'll notice that normally nail has just a random orientation of its domains. The magnetic domains are pointing randomly in all directions. Iron is a magnetic material, but the different regions within the iron have magnetic fields pointing in opposite or different directions, and they cancel out. But if you bring a magnet nearby, and you can see the magnet is in the hand right here, if you bring a magnet nearby, that magnetic field created by the magnet will cause all of the domains to line up with that field. It will then become magnetized, and then it'll be able to pick up these paper clips. Okay, that's it. So that's what did I talk to you guys about today? We talked about where the word magnet comes from. We talked about how magnets have poles. They always have poles. Magnets create magnetic fields. And then lastly, that magnets are created from moving charges, which gives rise to these domains ideas. Now this kind of makes sense if you look at this picture. Like if you have a magnet and all the domains are lined up, then if you break it apart into 2 separate magnets, then you'll see that it's still going to act like a magnet because all the domains are still lined up. So it's just going to act like 2 smaller magnets. And you can keep breaking that down, down, and down, and down until you get to a magnet that's literally just a single atom that's spinning around with a north pole and a south pole. Okay, that's it. Have a great day, guys. I'll see you later.